The fundamental principles that we will use in this lab are Newton's second law, the energy principle, which states that unless there is any work done on the surroundings, the energy must remain zero. We also must use the velocity update formula, the position update formula, the kinetic energy formula, the spring force formula, the gravitational potential formula, and the spring potential formula. To start, I took the video from Canvas and then imported that into Tracker to start tracking. I track the movement of the mass, and I also have some initial conditions. The initial position that I found was 0, 0.733, 0 meters. I also found that the object's initial mass and final mass was 0.402 kilograms. The initial length of the spring was 0.7 meters, and the initial velocity was 0 since it started from rest. Here you can see the movement in both the x and the y coordinates of the object on the end of the rope and spring. I then used the period of oscillation in the y direction to solve for k. And then from there, I was able to solve the L naught, or the initial length of the spring. For k, I found that it was 6.83 newtons per meter, and for the initial length, I found that it was 0.123. Next up, we are going to start looking at the computational model that we used using GlowScript on the computer. First up, we had to go in and introduce our initial conditions, which we've already talked about. Just enter those into the code. Next, it gets a little bit more difficult. We had to define our system and put in our equations so that it would do the calculations for us. As you can see, each of the different energies, the kinetic energy, the gravitational potential energy, and the spring potential energies are all listed here in a way where they can be solved for and then stored for later. We keep going to update these energies and our position and velocities, and then from there we can use this to find everything that we're looking for in the end. After getting all of our code right and entered, we then have to enter our .csv file into our code, and then from there it will run and it will compare our actual observed data versus what the computer runs. And as you can see, they are pretty similar in both ways. The y position is slightly more similar, and that is likely because we solved for the period k and our L naught using our y period instead of our x period, which is why that might look a little bit off, and that could be a potential error. Some other errors are that I could have used Tracker slightly wrong and tracked slightly off of the actual positions. The system is actually also not a closed system, so there could have been other forces working on the system that were not calculated in our model. In order for the energy principle to be satisfied, there has to be the same amount of energy lost as there was work done on the system. And since there was no work done on the system, the energy should remain zero. After looking at our graph here, you can look for delta E, which is the change in energy, and you can see that it remains constant on the zero. Because this is true, we can say that yes, the energy principle was satisfied. Finally, we were asked to discuss the difference in the periods between the x period and the y period. The way that I solved for this was taking the amount of times it takes to go 3 full oscillations and solved for that, and then divided by t to find the total period. In the x direction, I found that the period was 1.6 seconds, whereas in the y direction it was 1.5 seconds. This is only a slight difference, but this is what we use to solve for k, so this does have an effect on the whole rest of the problem.